What did they say? Mangyarang
About time. Joe almost made me for you.
Well, I texted Joe and Chula. She was not even in Maple Grove yet. They left at 6:30.
Are the roads bad?
There's an accident on Broken Boulevard on 94.
Oh my God.
He'll probably be here in another hour.
Oh boy.
Joe was saying, Joe,
Okay, do me a favor, please. Let's talk a little bit about cooling systems. I'm going to start cooling systems. I'm going to start with very, very important topic, really. And my start point, I would like it to be right here. So chapter 21 talk about cooling systems. Cooling systems, Jeff, my friend, has four very important distinct parts, guys, for the cooling system. So the cooling system is made out of, number one is the evaporator. You're looking at the evaporator, number one. Number two is the compressor. And number three is the condenser. And number four is that tiny little, expansion valve. So yes, we are electrical contractors. Yes, we do the electrical part of it. But you have, Adam, my friend, it's very important to understand how we cool a building. And this is all about cooling a building.
we do the controls.
We do the control and we do the power. Let me just explain a few things, guys. So, Jamie, my friend, what happened is the most important part of a cooling system is something called evaporator. You guys heard about the evaporator? What happened is let's do the electrical part of it. Where are we located here? So let me just throw a couple of things here. The first thing you need to do is there's a fan here, and my fan need a disconnect and an overconduction device. So here's my interface with this system, Aaron. I have a fan, and the fan, so what happened is we have this so-called evaporator, and the evaporator has refrigerant, a liquid that capable of absorbing heat. Refrigerant is a liquid material that's capable of absorbing heat from the surrounding atmosphere. So that's what a refrigerant is. So they have this refrigerant, guys, that's in the form of liquid, going through these thin coils that's called evaporator. And then to expedite the moving through the coils, you know what they do? They have a big fat fan, which electricians have to wire and provide a disconnect for, overconduction device disconnect. That's us. So you have this fan, the blower. The blower blows the air right through these coils. When the air goes through the coils, it picks the heat from the air, right? The refrigerant is capable of picking the heat, collecting the heat from the air. So when it collects the heat, from the air, from the other end, what do you get? Cold air. And that's what you're looking for, cold air. Can you have thumbs up, Chad? We fully understand that as you move the air through so-called evaporator, which is just these coils that full of refrigerant, you throw the refrigerant is going through these coils, you throw the air right through it, it picks the heat from the air, removes the heat from the air. From the other end is cool air, and that's what you're looking for. From the other end is cool air. Can I have thumbs up for that particular one? Now, how do we move the air through the refrigerant? We move through a blower. This is where we interface, Jeff. We come as electrical. We throw the air, so inside the building you have to have a blower. The blower is going to blow the air right through that called evaporator. The evaporator has the refrigerant going through it. It picks the air, the heat, right? From the other end you get cold air. Then when it picks the heat, guys, then you bring it. So then the liquid, because you're heating the liquid, turn into gas. Can you see that? Low pressure gas. So because the refrigerant liquid, as it picks the heat, collects the heat, store the heat, it changes status from liquid into gas. That's how they do it. So you enter as a liquid, you exit as a gas. Make sense? As a gas, a low pressure gas. Cool. And what happened? How did the liquid change into a gas? You collect all this energy, the heat, dump it right through the refrigerant, come as a gas. Then we have the compressor. The compressor will compress it, lower, increase the pressure on it. So the temperature goes down when you increase the pressure, and it changes into, look at this, from low pressure into high pressure. When high pressure, now we have high pressure gas full of heat, hot, high pressure gas hot. So you throw these high pressure gas through the condenser. The condenser is, again, multiple coils, and then your electrician will come over here. Oops, my electrician will come over here, and here's my electrician, will come over here, put a disconnect and overcaptation device, right? Here's another blower. Outside, blow the air right through this condenser to remove the heat from the liquid, to remove the heat. So this is hot air, hot air. Does everybody see how the hot air comes from here, collects through the refrigerant, and gets out to Mother Earth? Does that make sense? Does that make sense? The process of removing air, hot air from the room. If you remove hot air from the room, Jeff, you basically cool the room. Make sense? You basically cool the room. Any question guys where we interface? Then another interface is also you need a compressor. What do you think the compressor is going to need? A disconnect and overcaptation device. All these points are our interface with this mechanical system. Our interface with this mechanical system. One more time. The liquid goes into the evaporator. You blow air. Hey, you blow air through this evaporator. You collect the heat. By collecting the heat in the liquid, Aaron, it changes into a gas, low pressure gas, because that's how it changes. It collects the heat. It changes status from liquid into low pressure gas. The compressor will pull the low pressure gas. You need a pump to pull it, as well as increase the temperature, increase the pressure on it, reduce the temperature slightly, so reduce its temperature, and then change it into high pressure gas. Throw the high pressure gas, guys, into the so-called condenser. The condenser is just coiled, Jeff, like this, and you're blowing right through. A blower is blowing air right through it, and by blowing air right through the hot, high pressure gas, you get the air out of it, you get the heat out of it, and when you remove the heat out of the gas, what happens to the gas when you remove the heat out of it, the energy out of it? It changes back into what? Liquid, and you keep doing it over and over and over again. And then they have this valve, expansion valve, that controls the flow of liquid inside the condenser to control how much heat, how much cool you want in your building. Any comments, any questions guys about this cooling system? Very, very simple, very simple. In order to have a cooling system, the refrigerant, they call it the refrigerant cycle, Aaron. Refrigerant cycle is made out of a refrigerant that rotates. I don't know if you guys can see, high pressure. So you can see that you came out of here, and up here they will go through. Can you guys see? You go through here, and in this area, I hope I'm drawing it right. It changes back into liquid, and it goes back here, and here, halfway through, it changes it back into. Can you guys see that? This is where the liquid collects, gets into the evaporator, collects the heat, then you have cold air, remove it, the compressor pull it, put it right through the condenser, get the air, the hot air out of it, and you keep going over and over again. Any question guys about the major 4 components of a cooling system? Component number 1, you need the evaporator. Component number 2, you need the compressor. Component number 3, you need the condenser. And component number 4, you need the regulator, the expansion valve. Any comments, any question how the system goes? This is called closed loop cycle. Closed loop cycle because the refrigerant doesn't go anywhere. It keeps, right? The amount of refrigerant for the most part in this condenser compressor tank, it stays the same, guys. You keep just changing it from, it keeps going from liquid gas. Liquid means you can collect heat. Gas, you can remove heat. Liquid, collect heat. Gas, remove heat. Liquid, collect heat. Gas, remove heat. And that's how you cool a building. Cooling a building is the process of removing heat from the building. That's how they cool a building. Heating a building is the process. When you heat a building, you have to burn something to throw heat into the building. Cooling it is the opposite, removing heat from the building. Can I have thumbs up, Chad? Removing heat from the building is the cooling. So that's the principle of operation. Now this could be your air conditioning, guys. If you have a home air conditioning, here's what happens. This one here, Jenny, my friend, the evaporator is inside your furnace, right? And the blower is blowing right through it. That's inside your furnace. Then the compressor and the condenser are out the outside unit, right? And you can see if you ever stuck your head right above the furnace fan, you see the heat coming out of it. That's how they remove the heat from a house or a building. Any comments, any questions? Any comments, any questions? Everybody understand the basics of heating or cooling a building, basics of cooling a building. Now, they're cooling it through refrigerant. In small systems, guys, they use refrigerant. In bigger systems, like Dunwoody, we chill water. We chill water. So there will be two cycles. In bigger system, we'll talk about this one in an industrial project. In a smaller system, the refrigerant goes from your basement, Jeff, from your basement furnace into the outside unit of air conditioning. It keeps going recirculating. That's because it's a small unit. If you call Dunwoody, can you imagine how you're going to cool a building like Dunwoody? They do it with a chiller. So what they do is they chill the water, the same process with a compressor and a chiller. The chiller will have a compressor in it, chill the water, through a refrigerant, move the refrigerant through coils to chill the water. Then they circulate the chilled water all the way to the air handling unit. So this piece evaporator will be inside the air handling unit. Inside the air handling unit. The evaporator inside the air handling unit. So you put an air handling unit evaporator inside it, you blow the air through the evaporator is carrying water. Then the water will collect the heat from the building. You pump the water through big fat pumps all the way to the chiller, chill the water. Chilling the water is removing the heat out of it, guys, right? Remove the heat out of the water and shoot the water back again through another pump all the way to the air handling unit, and you keep doing it over and over and over again. So can I get you guys to give me thumbs up if you understand bigger systems, they use water. Smaller system, refrigerant, not big deal. Bigger system, they use water to chill the water and they circulate the water. They still use refrigerant, but instead of the refrigerant, guys, you throw the air right through the refrigerant to get the cold air. They use the refrigerant to chill water, and then they carry the chilled water all the way to different parts of the building in different air handling units, and then they blow the air right through that chilled water to get you the cold. Any comments, any questions about this? Any comments, any questions about this? Does it make sense? Now, my job and yours, Darren, is not to put the system together. If you understand it, you'll be better as a designer. My job is to come to the mechanical guy and say, where is your evaporator blower? This is your evaporator blower. I need to wire it. So you provide an overconduction device, a disconnect for the evaporator blower. Then my second job is to go, where's your condenser blower? You need a blower for the condenser. Where's your condenser blower? I need to wire it. So you provide a circuit with a disconnect and a conductor to the blower that blows through the condenser, right? And then the third component is, where's your compressor blower? You need a compressor, right? You need the compressor motor. So you need to power the compressor. Sometimes they power these two together in smaller units. You see that the blower and the condenser, blower and the compressor are powered from 120, 140 amp, 30 amp circuit typically, right? And then, so that's the power. Then what they do, guys, is they have control. They have control system that goes between all these. I'm not showing the control. What color should I use here? But there will be a control system that going from between, I'm just going to say, so there will be a controller here. Controller, and you're going to have a controller here too, controller, and then there will be a controller here, and these guys are talking to each other. These controllers are talking to each other. Okay, that's your class 2 circuit. That's your class 2 circuit. Any comments, any questions? So we have 3 power circuits. Power circuit number 1, power circuit number 2, power circuit number 3, and we have another class 2 circuit that they talk to each other. They talk to each other. Any comments, any questions, guys? That's, in a sense, the basics of cooling system. The basics of cooling system. And how do we interfere with them? We need to power these equipment. Control, typically they do the control, guys, the mechanical contractors, but you might pipe it for them, or you might be the guy who's hired by the mechanical contractor as a designer to design the control system for them. So then you have to have conduits that carry the control separate from conduits that carry the power, and so forth. For your air conditioning, the residential, you see that wire, the thermostat wire going to the air conditioning, right? And the thermostat wire that's coming from to the furnace, between the furnace and the air conditioning, and between the air conditioning and the thermostat. Now in a bigger system, guys, there are more wires to carry the signals and adjust them. Any comments, any questions? So that's basically the basics. So let me go through a couple of definitions, guys, and since we understand what the system is. So so that's basically what the chapter. I started with a nice picture for it. So we're going to talk about the cooling system parts. Now we know the cooling system parts, the 4 parts of a cooling system. The function of each part. We're going to just one more time from the condenser, evaporator, condenser, valve, and compressor, what each one of them does. Necessary calculation to obtain the size of electrical components. Some calculation to size. We need to be able to size, guys, the conductors. For us, electrically speaking, I care about the following: overcurrent protection device, conductor, disconnect, and machine. These are the things that I need to be able to size. Number 1, number 2, and number 3. I need to be able to size these number 3 things for a motor. I don't care. Well, I care, but I don't have to know what the motor is doing as long as I have this information and I can size these 3 things for that motor or compressor. Excuse me. Typical wiring diagrams, guys, especially the control diagrams. We'll look at a couple of things and shows how the system operates. That's your control circuit. So this is basically, let me tell you a story. This is real, Zach. When I first started doing design, I was confused between the chillers, the boilers, and the air handling unit. Confused. So we were working in a hospital. It happened to be for Mayo Clinic. Got in the building, and I know how to size the stuff, but I didn't know how these equipments talk to each other. So I went to a mechanical engineer, and they said, explain to me how a chiller talks to a cooling tower, talks to a boiler. So basically, how do you heat a cool hospital? So I sized everything before I knew how these systems interacted. So I sat with that mechanical engineer, he explained it to me, really cool. So when you understand it, my point is, when you understand how the system is put mechanically together, you'll be a better designer. So as you start working, it's really partner with the mechanical engineer, because that's their job. We don't size the refrigerant. We don't size the compressors. We don't size the blower. All these are sized by mechanical engineers. There's a whole lot into it. Sizing the pump to be able, the speed of the water inside the pipe, the thickness of the pipe, all these guys are sized by mechanical engineers. Our job, guys, is to understand the system so we can power it. Cool, at least enough to power it. Okay, refrigeration. Refrigeration is as simple as the method. This is one of the most important definitions for it. The method of removing energy in the form of heat, from an object. So your refrigerator, guys, when it chills, the same thing, refrigeration cycles, you can use refrigeration cycle guys, for refrigerators to chill things, or you can use to cool building, right? It's the same process, to remove the air from inside the fridge to the outside. Same principle, refrigeration cycle they call it. Refrigeration, removing the heat. Because removing the heat, this boy, the evaporator, you guys remember that evaporator inside the building is the single most important part of a cooling system, because that's what sits inside, and you take the air inside this room, blow it right through this evaporator coils. They're basically pipes, loops of pipes. You blow it right through it. It collects the heat because it's touching the air is touching the pipe. It collects the heat from there and changes it from a liquid into a gas. It gains heat, and it's like boiling it almost, right? Boiling the water, that refrigerant, into a gas, change it into a gas. They use special type of refrigerants that can collect heat much better than water in this case. Okay, so that's your evaporator. commercial building evaporator process is controlled by closed loop. The second thing that we looked a minute ago, guys, I showed you that closed loop. That refrigerant keeps going between the evaporator, the compressor, the condenser, and the valve, and it keeps going into a cycle. Keeps liquid, gas, liquid, gas, liquid, gas. Liquid means hot. Gas means liquid means cold. Gas means hot. Remove the heat, and they keep through going all these cycles. So why do they have a closed loop? Because they don't want to keep filling the refrigerant is expensive, so they use it over and over, like compressor in your fridge. Same thing. The refrigerant stays there. Sometimes when you lose refrigerant, what do? They go fill it with a new refrigerant. But the refrigerant liquid, guys, stays into the system. It is used over and over in so-called refrigeration cycle. Refrigeration cycle. Any comments, any questions, guys, about the refrigeration cycle? The process of removing heat from the building. Removing heat from the building. And we looked at it. Okay, if you graduate from your friends done with not knowing these, you're in trouble. Here's number 1, number 2, number 3, number 4. Number 1, guys, we said evaporator's job is to be inside the building and you throw the air right through it and collects the heat. This guy collects heat. Collects heat. Right? The compressor is increased. The compressor, so the collects heat. The compressor's job, guys, is to pump refrigerant, and increase pressure. Pressure. Pull the refrigerant and increase the pressure through it. The condenser, the condenser is remove heat. Remove heat, right? And the expansion valve is control the liquid, control liquid flow, control liquid flow. And in terms, Jeff, control the process of cooling, how much cooling you want. Any comments, any questions, guys, about these 4? I guarantee you these will be on the final too. The definitions, just definition, what they do for living. Any comments, any questions about these? How many spelling mistakes did I make? A few? Okay. But these, the most important things, guys, this guy collects the heat. The compressor take the collected heat, right, and compress it, increase the temperature. The condenser remove the heat, and the expansion valve control the process. And when you're in the picture, you guys, it's very clear. Here you go. This is the picture that we're looking at. This guy collects the heat, right? This guy removes the heat. This guy increase the temperature and pull the liquid through it. And this guy control the flow of the liquid, and in a sense control how much you cool this building. Any comments, any questions about the process? Next project, Jeff, what we do is I bring one of our friends here from the mechanical guys, and they'll go over a cooling tower, something called cooling tower. Instead of cooling with air, we start cooling with water. For bigger buildings, they start cooling with water. So that's what we're going to be talking. Evaporators, we'll talk about the evaporators, guys. Installed normally consists of a thin tubes, that's coils, exactly. It looks coils like these, not electrical coils, through which the building, and then you circulate the building air right through it. So coils, mechanical coils, pipes, and you circulate the air through it to collect the heat. Function, remove heat. What does it do for a living? It removes heat. From the interior of the building to the exterior, removes heat. Thumbs up, Chad? Okay, cool. So with that guy removes the heat. Compressor is pump. What does it do for a living? It pumps. Remember that low pressure gas have to be pulled. So who's going to pull it? The compressor will pull it and pressurize it. By pressurizing it, guys, it changes from liquid, from low pressure gas into high pressure gas, in a sense reducing its temperature, and then shift it right through the condenser to remove the air from it. So refrigerant from the evaporator boosts the pressure, so draw. Then the second thing is boost the pressure and send it to the condenser. Can you guys see what it does? It pulls the gas from the evaporator. It pump it, increase the pressure, in a sense reducing its temperature, and it shift it back to the condenser. Now we have a reduced temperature, not completely reduced, but reduced temperature, still have heat, and then you blow the air through that reduced temperature, high pressure gas to remove the heat into Mother Nature, and change it into liquid, and keep doing the process over and over. Direct compressors are usually used in large, direct driven compressors, so motor driving the compressor right away. The term that they use, guys, is hermetically sealed compressors. Hermetically sealed compressors, these are the term that they use to have, what they do is that cold air goes right over the motor that drives the compressor, it cools it down. They're all built into one big box where the cold air goes right over the motor and cooling, in the process cooling it. So that's my evaporator. Okay, so Jeff, here's what you're familiar with. The compressors are usually air-cooled units. That's the one I have in my house and your house, and a lot of you guys. So that's very common. You go to a bigger system, they start using water. This is when it becomes, next project, guys, we'll look at a cooling tower. So they're using a cooling tower with circulating water to cool the condensers to cool them, instead of air, just throwing the air through them. You put water through them to cool them, okay? And then evaporative cooling units, that's another system that they use. I'm not familiar too much with it. So either air and water, air we know, blowing air through it, water is putting water through it, it cools it down. The whole idea of the condenser is to remove the heat. Remove the heat from the high pressure gas and throw it outside. And then the condenser condenses the refrigerant back from a gas after it removes the heat from it into a liquid, and send it back into where? To the evaporator to do the process over and over again. Any comments, any questions about the mechanical part of it? The mechanical part of it before we jump into the electrical part. All this is FYI only. The more you know it, the better. But really, nobody will ask you to size the refrigerant for a building. You've got to understand it, though. You look like smart designer if you do. Okay, so that's basically the condenser. Expansion valve, guys, the job of the expansion valve is to control the process. So it's the inlet to the evaporator. It controls the liquid that's coming in. By controlling the liquid, you can control the cooling process, or part of it control the cooling process. Controls the rate at which the liquid flows into the evaporator. Cool. That much will give you that much cool. That much will give you that much cool. Controlling the process. How do they do this? They have a temperature sensitive bulb that activate the valve. This is just about how they do it. Sensitive bulb, it activates the process, guys, and open and close that valve. You can read the outlet of the evaporator senses the heat of the refrigerant as it passes through the evaporator. Senses the heat. Then the bulb is filled with the liquid, expands and connects to the back. So this is just describing how this valve works, guys. Diagram to cause the expansion valve to meter more or less refrigerant. So the liquid heat looks at how the heat, that bulb, temperature sensitive bulb gets. If you give me that much heat, I'll open that much and I'll allow that much to flow through it. So that's the valve, explaining how the valve works. Typically, we don't specify the valve, guys. It's specified by our friends, the mechanical contractors. But that's how they do the expansion valves. Any comments, any questions? Explained by an electrical engineer, just for disclaimer here. Any comments, any questions about that? Okay. Hermetic compressors. If the term hermetic compressors, guys, is really interesting. This is how they define it. Consists of a compressor. It's a combo compressor motor completely sealed in a gas-tight steel casing, all in one gas-tight steel casing. Who cares? If it's a hermetic compressor, Jeff, we can allow this pump to work much harder than if it wasn't, and you're going to know why. They separate them from other pumps. the compressor is completely separated from other pumps. The reason for refrigerant gas, look what they do. They use the refrigerant gas, guys, circulated through the compressors and over the motor winding. That's what I want to do. That's why it's a special type of motor, and an NEC code book assigned 440, Article 440 for it, because they use the refrigerant, the gas refrigerant, as it comes and circulate over the coils. Now, enemy number one of motors is what? Heat. If you can use the gas to heat the windings of a motor, you can you can overuse the motor. So long story short, these type of motors are horses. They can work much better than any other motor because they're cooled with refrigerant gas. And also the rotor, and also the bearings and the shaft. All these are being cooled as part of the process. Who cares? What cares, guys, it makes a special type of motor that the NBC could book allocate a whole article about it, 440. Can I have thumbs up, Chad? That's all we care about. Every time we hear the hermetic compressors, we understand it's a compressor driven by a motor in one big box, where the compressor is actually using the coolant to cool the motors too. So we can abuse them a little bit. Helps. So when you circulate the coolant, the gas, guys, what does it do to the motor? It helps cool the motor, and that's the single most important thing. Why it's a special motor? Because it's cooled by the nature of the process. Versus if you have a fan, Darren, if you have a fan right there, there's nothing, no refrigerant is going on the coils of the fan, so I can't abuse that fan. It's going to get hot. You know, in this case, they're all in one box, and they allow the gas to go right over, by design, over the coils and the bearing. It cools it down. And if you can cool any electrical or mechanical equipment, you can get a lot of energy out of it, right? Because heat is enemy number one of electricity. Period. Any comments, guys, about this special? The only thing you need to remember, if you forgot everything, remember, if you have a hermetic compressor, meaning a hermetic compressor, you have to apply the rule of 440. So it's not 430. It's not 430 anymore. It's not 430 anymore. Okay, so here's how they do it, guys. I don't know if you can see. They take the gas over here, and so they circulate it over the windings and high pressure gas. So they circulate it, it cools it as it goes out. It cools the winding as it goes out. Now, designed by the manufacturer, that the gas, the low pressure gas, circulate over the windings to cool it. As it enters the compressor, it goes over the windings. Can you see that, Jeff? As it enters the compressor, it goes through over the windings, and it cools it. That's all what you need to know. It cools it. Cools the shaft, the windings, the bearing, and so forth. Okay, cooling system control. Here's how, now back into the cooling system control. Here's the control system, the cooling control system, guys. You can see these are your class 2 circuits. Class 2. This is my class 2 circuits. I'm not going to go through all the control. I'm going to remind you a couple of things. You can have high pressure. Now, when you have a compressor, what's the problem with the compressor, guys? The compressor is you're creating a bomb. If you keep putting more and more pressure in that tank, what's going to happen to it? Explode. So they have high pressure and low pressure. High pressure and low pressure, very, very important every time you have a compressor. You need to protect from high pressure or low pressure, because you don't want to damage the equipment or make it explode, right? So they have a lot of high pressure and low pressure. They have also temperature safety. There's a lot of safety equipment. And here's your control, where you can call for a heat to get you the heat and cool in this case. And you have a circuit, a control circuit. This one for us is to power the controller. This is my controller. This is my controller powered and interface with the compressor to turn that system on and off, I have a better picture that can go over it a little bit more details on that one. This is about the project that we have, guys. We have 2 types of cooling system for this. They call it, one type is called single package unit. Now you're getting into the types of the cooling system, single package unit. The other type is split package, split system. The other type is split system. Cooling single package unit, guys, you have one unit, and it feeds, we'll look at it in a second here. One unit that everything is in that one unit. It's like window air conditioning. Does that make sense? When you have window air conditioning, that's a single unit. When you have a split unit, is like you have the one in your house, right? You have the coil in the basement and a compressor is outside. That's basically a split system versus single unit. So these are the system that they use for this. Compressors and condenser located on the roof and the evaporator. So the split system, the condenser and the compressor on the roof, like my house exactly, and the evaporator somewhere in the building. Any comments, guys, about these? They call them single package unit, rooftop units is another names for them. Okay. So if you have a split system, then you have to have ducts, right? Like we do, so you can bring the coolant all the way down. So ducts system must be provided to connect the evaporator with the area to be cooled. Duct. Electrician, you have to provide, what do you need to do? Power all these units. You power the units. And we also provide wiring to the thermostat. A lot of application, guys, you pull the wires for the thermostat. For bigger systems, we put the pipe, and mechanical contractors will pull all their conductors inside it, all their control system inside it. All their control system inside these boys. Okay, here's a split system, guys. Here's a single unit way at the top. I don't know if you can see. This is a single unit or rooftop unit. Sometimes they call them single unit. This one is split unit. The evaporator will be somewhere. I don't know. We're showing the evaporator. Here's the evaporator here, and pipe all the way down, and so the condenser. So there are two types. So these pieces, this one and this one, split unit. Two parts, one inside the building, one outside. This one, single unit, all of them are outside. Can you guys see here? And you get the air in, you cool it, and you remove the heat in and out, right? You do the whole thing in one. It's like window. Think of it, window air conditioning. What does your window air conditioner do? Takes the air, cool it, take the heat out of it, throw it outside, and bring it back, and keep removing the heat from the room. If it's split unit, it's very similar to having central air conditioning, what we call central air conditioning. Any comments, any questions about these two systems? Any comments, any questions? These two systems. I will remind you, this is a nice picture to remind you guys with the powering the equipment and providing power and control for your equipment. Power and control for your equipment. Okay, now moving into our electrical part, guys. An EC code book. This is the article that talks about the refrigerant. Anything that has refrigeration cycle and a compressor, you are to use Article 440. Involved with more than, so the key point is that you have a hermetic compressor. Hermetic compressors. Look at the installation of air conditioning and refrigeration equipment involving one or more hermetic compressors. You must use Article 440. If it's not involved, then they refer you to Article 430 for motors and Article 422 for appliances and Article 424 for heaters, I believe. So, gentlemen, if your equipment has a compressor, typically hermetic compressors, like we talked about, this article is completely associated with this so-called hermetic compressors. Why? Because it's a special type of an equipment. Otherwise, this article for motors. So every time you have a compressor, most likely you have hermetic compressors, and you apply the chillers, and you apply the rules of the Article 440. Any comments, any questions, guys, about this? So the key point for using Article 440 is hermetic compressors. You're chilling things with a compressor. Okay, there's a couple of adjectives that they use, guys, to describe it. Now we're talking electrically speaking. Now you can wake up. Electrically speaking, everything that we did is mechanical. Electrically speaking, they have locked rotor amps. These are very important terms. And if you guys go to Chapter, special terminology, page 474. Locked rotor current. We have the term number 1, number 2, 3, and 4, 5, and 6. So I'm going to pick out of these the most important ones, guys. Maximum overcurrent protection device. This is the single most important thing. Here's my overcurrent protection device. This one is 100 amp. This is called maximum overcurrent protection device. Maximum, this is, I'm going to call it, this is number, which number is that? Number 4. Okay? So, Jeff, if they told you on the nameplate, maximum overcurrent protection device is a fuse, you put a fuse. If they say circuit breaker, you put circuit breaker. Done. Right on the nameplate. Can I have thumbs up, Chad? We do that? Okay. So the maximum overcurrent protection device. The second one is minimum, we don't have a rated load amps, overcurrent protection device. Disconnect means rating. We'll talk about disconnect means rating. Disconnect, guys, when you come over here, you have to have a disconnect, right? That's number 6. The disconnect rating, Jeff, has 2 ratings. Number 1, amp rating. You have to have an amp. And number 2 is horsepower. So your motor, it's like any other motor. Your motor have to be able, your disconnect have to be able to disconnect the amps and the energy coming out of this air conditioning. So we got the overcurrent protection device, maximum overcurrent protection device, overcurrent protection device selection. So that's also, is it a fuse? This one is it a fuse or a circuit breaker? Disconnect means, we talked about disconnect means. These 2 values, guys, these 2 are used to size your conductor. So you take the largest of the 2, multiply it by 1.25, and then you size your conductors. One more time. Rated load current, the largest amount of current, this is the amount of current that the system is going to draw while it's fully loaded. Rated load amps or rated load current. Minimum branch circuit selection current is another value that they use it, guys, because the system has multiple things running, relays and blah, 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 compressor and fans. There are 2 values here. If they give you the rate, this is a full load amp, basically. Very full load amp. Either it's given as rated load amps or branch circuit. When you get it, you multiply it by 1.25. What do? You size your conductor, whichever is larger. Locked rotor current, that's if your system is not, if your system is to stop. That is the largest amount of current that your system is going to draw if the rotor is to be locked. Hold it, unlock it, and that's the largest. It's inrush, basically your inrush current. Your inrush current, locked rotor current, the largest amount of current that the system will pull if the compressor is not to work. It's stalled. Any comments, guys, about these terminologies that they use? Any comments about these terminologies? So these are a few terminologies that they use. I can't emphasize the most important ones for sizing. We talked about number 4, and we talked about number 2 for the conductors, number 2 or 3. For the disconnect is number 6 that we use to size these equipments. Okay, so that's basically the branch circuit and full load examples. We talked about these one. There's also another term that they use, guys. They take these and they call it minimum circuit ampacity, and they size the conductor directly. So Jeff, what they do is they take 1.25 times rated load amps and then equal minimum circuit ampacity, and they put this value for you. So the manufacturers themselves, they take the rated load amp of the equipment, multiply by 1.25, and they put the value as MCA, minimum circuit ampacity. And then you use this one directly to size your conductor. So if you guys remember the chiller that we had, it has minimum circuit ampacity of certain values. You're not supposed to multiply by anything. If it says MCA, minimum circuit ampacity, they already did the calculation for you. Cool. The overcurrent protection device, Jeff, here, the same thing, guys. What they do is they take 1.75, multiply it by rated load amps, and then if it's not a standard, they go down, and then they give equal maximum overcurrent protection device. That's how they do it. To summarize, the manufacturer will give you guys 2 things. maximum overcompression device, and minimum circuit amplicity. These two values are always given. If they're not given, Jeff, how do you do it? No problem, Chad. Rated load amps times 1.25. Done. If this is not given, how do you do it? No problem, Chad. Rated load amps times 1.73 is 75. And go down if it's not standard. Any comments, any questions? Any comments, any questions? We did calculation, guys.
Is it different for the hermetic motors then?
These are
Here
for
we're
hermetic.
talking 225.
If it doesn't work, very good point. Very good point. If it doesn't work, if you use 1.75 times RLA and you're still tripping the circuit breaker, then you go to 220. What is it? 225. Yep. 225 is the exception. This is the rule. Good point. If this system doesn't work, guys, we use 225. We use 225. Any comments, any questions about this? Any comments, any questions? So we size, what I do usually, guys, in the spring, we do the whole system for a chiller. We size all the stuff for chillers and so forth. Okay, air conditioning, disconnect means, when it comes to the disconnect means, like we said, guys, very easy. You take a rated load amp, multiply it, Jeff, by 115, 115%. Exactly like any other motor. Exactly like any other motor. 115. And also the disconnect have two sizes. The other size have to be based on horsepower rating. And how do you find the horsepower rating? Based on this equipment right here, horsepower rating. And I'll show you an example in the list in a second. Very easy, very simple, very easy, very simple example to use. Okay, so for disconnect, when you have a disconnect, guys, your disconnect is going to do the following. Here's my disconnect, and here's my equipment. It's going to have two sizes. This disconnect is 30 amps and rated for 10 horsepower. Can you guys see the two sizes? Amps and horsepower. Amps allow the current to go through it. Horsepower allow you to, in an emergency situation, to interrupt the energy, load interrupter, so it doesn't blow up in your face. This is typical for motors, guys. Motors are the same, like these. Exactly. It has to have two sizes. Amps and horsepower. Amps and horsepower. When you size them. How do you size the amps, Chad? No problem. 1.15 times rated load amps. How do you size the horsepower? No problem. Horsepower. And if you are given the horsepower, you can go to 430.250 or something like this. If you are not, from the locked rotor current, you can go directly to this table, and I'll show you in a second. Two ways horsepower sizing. Either from the horsepower, 430, that give you the, you're already given the horsepower, or if you don't have the horsepower, guys, we use locked rotor current, and from table 430.251, you find the horsepower rating of this equipment. And with some, if you have, this is really interesting. If you have a disconnect that feeds two motors, right? Disconnect that feeds two motors like this. So here's my rated load amp 1 and 2. How do you size the disconnect? Very easy. The way they size them, they take 1.15 times rated load amp 1 plus rated load amp 2. See what they do? They add the amps and multiply them by 150. Very easy piece of cake. That's the amp size. The horsepower size, very easy. Suppose this is a 10 horsepower and suppose this one 20 horsepower, right? So the way they do it, guys, they take 10 plus 20 and you go to table 430 dot, so we have to, it has to be rated to handle both of them. 430 dot, actually you take the full load current. There's two ways of doing it. You take locked rotor current 1 plus locked rotor current 2, and then you go to the table 250.251 430.251. 430.251. So you take the two locked rotor currents and size the disconnect, add them up, and size the disconnect to carry them. I will have calculation for you in the spring. I just don't do the calculation now. We will do calculation in the spring, guys, how to size them. If you know it now from the book, great. Really, no rocket science. You take the locked rotor current here plus this, go to the table, size your conductors. You size your disconnect, horsepower-wise. We talked about the horsepower checking. Okay, what does a horsepower size is? This is my favorite. Means a horsepower size, here's what it means, guys. Means is capable of safely disconnect the full amount of current. That's why they call them horsepower rated. So if I see the process as being, like this disconnect right there on the wall, and a motor is plugged in and the motor is smoking for whatever reason, I can use it as a safety switch and shut down that circuit breaker. Or I can see something is, out of the ordinary going in the motor. If there's no emergency shut down, you can use it as an emergency shutdown. It's not meant to be a controller, but you can use it as an emergency shutdown safely. If it's not horsepower rated, Jeff, you know what happened? It will explode in your face as you open it. And guys, we're not talking about 1 horsepower, 2. We're talking about 400 horsepower motors, 500 horsepower motors. Really? You go disconnect the circuit breaker, and it will explode in your face if it's not rated to interrupt this energy. Any comments, guys? Any questions? So that's your equipment here. Overcome detection device not to exceed the value indicated on the nameplate. This is the most important things for the over current protection device. Like we said, overcome detection device, the maximum overcome detection device. The controller, this article does require you, the controller, to be rated to handle the short circuit, withstand rating. So if I have a controller, I need it to be able to withstand the short circuit. That's how it tells you. You don't want it to explode in your face if they have a short circuit. Overload protection. Overload protection and the compressors, motors, guys, always provided by the manufacturer. Typically, Joe, my friend, inside the chiller, the overload is set completely as part of your controller. We rarely, if ever, size an overload for a chiller or a compressor. Look at the air conditioning. All comes in that box. All what we provide is just a power to it and a control circuit. All the load and a disconnect. The overload is provided by them. Why do you think they provide the overload? Because the compressor, guys, has a lot of things. There's a compressor on the motor and all these relays and controllers and transformers that transfer to control voltage. So there's more to it than just a fan. Okay, so they provide the overload. Overload is always, guys, requires 52 requires compressor to overload and failure to start. That's what provide 4452 provide overload protection and short circuit protection for your system. The last thing about this, guys, is tons versus amps. They give the chillers in tons, 500 tons, 600 tons, 500 tons. What they do is they're a value conversion value that you use to convert. How are you going to take if a 500 ton? What's a kW? So my job and your job is to take the tons here and convert it into kW at a certain power factor, so that we can get the kVA, so we can size everything else. So how do you go from tons to kW? Always consult the manufacturer's literature. Always the manufacturer's literature about chillers and compressors, they have the tons right next to it, the kW, and the power factor, or the kVA. So because with tons, sometimes it goes 1-to-1. A ton is equivalent to 1 kW. Sometimes a ton is 0.8 of a kW. So every manufacturer. So what I did, typically, if I don't have this value, guys, work in an engineering firm, you either call a manufacturer or consult one of the mechanical engineers. They have standards that they convert them. So if they give you a chiller in tons, your first job is to, how am I going to convert this to kW? The software that we had, remember guys, the software that we had, Cummins, you can put it in the software and there's a multiplier that they get you. I don't know if you guys can remember. That software can help you go from tons into, you start putting kW until you get the actual tons, approximate value of tons. So, but remember, it's a mechanical value that you have to get from the manufacturer or the mechanical engineers. When I worked at the LB Beckett, we always get these. When we go to the mechanical engineers guys, the first thing they give you is, here's our tons that we love, and right to you, Chad, here's your kW and volt amps. And then I take my volt amps and run with it. Any comments, any questions? But be aware, the bigger the ton, the bigger the units. 150 is smaller than 500 ton. Okay, so that's basically what this article. I'm just going to show you a couple of pictures, guys, and let you go here. We talked about this one for those of you who were here. This is really the bread and the butter of the whole system, starting from the evaporator into the compressor, condenser, and going back through this loop. I hope it was clear how the system is put together. Here's the different pictures, guys, of the chillers, the coils. They call them coils. The condenser or the evaporator coils. So you get the refrigerant to go on one side and come out of the other side, hot or cold. So these are a couple of coils. When we say the coils, and your job is, let's say here come in, here come out. This coil, let's just say this was a coil for, this could be a coil for the evaporator or a coil for the condenser. Looks the same. And your job is to blow the air out of here. So let's just say this coil we're bringing hot, taking cold. So this is blowing the air going in. This here will be hot air. Hot air. If it's an evaporator, it will be the opposite, cold air. The evaporator will be cold air coming out of it. Okay. So these are the coils. Remember, the coils are different. Rooftop units, similar to this, guys. You're going to see them all the time. Split unit, or here's a whole compressor. This is a unit. This is air conditioning. For commercial building, they call them rooftop units. Big fat air conditioning on the roof, right? Either split or single unit, one package, or split packages. Here's your this one is very clear. Oops. This is really cool. This is your condenser. This is your condenser, and what they do is they blow the air into it, and you get exhaust hot air. Can you guys see that? So this is my condenser. I get what they do is they get gas here. This is hot gas coming in from the evaporator, and cold liquid coming out to the evaporator. And your job is to have big fan like this, pull the air out, suck the air right through it. So it takes the air from Mother Nature outside and take the air right through these coils. Can you guys see how it puts it right through the coils? You've seen in your air conditioning. And out of here comes hot air. What they do in integrated system, guys, they take this hot air and they heat your water in the winter. So that's how you take advantage of every single unit of energy that you have. So remember, that hot air is thrown up in Mother Nature, right? What if you can capture this to heat your water? Domestic water, right? In the summer, because we don't use air conditioning in the winter. We use it in the summer. So I don't need to heat the building, and we use it in the summer. I don't need to heat the building in the summer, but I still need to heat the water. So what if you capture this and heat your domestic water? So that's how they get into a whole complicated system. So that's what this condenser is going, in this case, condenser. This is a really nice picture of it. Look at that cool water comes in here, hot water comes out. So the hot gas coming in, and this is how they do they chill with water. They chill with water. If you have an air handling unit, you have the hot gas coming in. I don't know if you guys can see that. Here's my hot gas coming in out of the evaporators coming in from here, and they put the gas in here, and at the bottom going back to the evaporator here as a liquid. And instead of chilling it with air, they circulate water, cooling water. They have cooling water and hot water. They circulate with water. That's where you have your cooling tower. Promise you, next project when the industrial will have a cooling tower. That's where your cooling tower is going to be located. Take the hot water, cool it outside, and refrigerant. So it becomes the air, guys. At one point, air becomes not enough to cool the system. Just not enough. The building is too big. When the air circulating of the air is not enough to cool the system, the refrigerant, they smarter than Chad. They come and they use water. Water can cool better than air. And then, believe it or not, if that's not enough, they use a cooling system to cool the refrigerant. So a cooling system to cool another cooling system. So it gets more complicated. The idea is you want to remove energy from this gas, fast, efficient. The easiest way is air, but for bigger systems, it becomes very expensive to use air. So they use a cooling tower. They circulate the water with pump, cool the gas. The gas continues to chill another water cycle, and they take it to a big tower here outside with big fans at the bottom, and they cool the water. They cool the water outside either by using water or by using air. So it gets a little bit more complicated what they can use. Okay, so here's water drips. So cooling air go through water, cooling it through water. So different ways of cooling, like I said, refrigerant. Okay, so that's basically what I wanted to show. Your control circuit. The control circuit, guys, gets very complicated, and I wish we teach you in the control here. But really, the bottom line is you get into, here's your thermostat here. You can see your thermostat if you put it in cool auto. He's typically heat and cool on the same thermostat, of course. I don't know if you guys can see the evaporator fan motor control. I'm just going to focus on these, high pressure and temperature and low pressure. These are your safety factors here. And there's a couple of fans here with fuses, overcome protection device. All this, guys, is part of your compressor, air conditioning cabinet here. CM is my compressor motor. Here's my compressor sitting right here. And we have the evaporator fan, evaporator fan relay, evaporator fan motor, condenser fan motor. So there's a whole lot of package. You can see, guys, why a unit like this 2A three-phase supply from power is more than just a motor. There's tons of things inside that unit. So your job and mine, Jeff, is to come over here and provide that disconnect way at the top and the overcome protection device and the feeder. Everything else will be wired internally. We also provide the wiring, the thermostat wire class 2 circuits here. Any comments, any questions, guys, without turning into a control? We typically teach this in control, go in details, but I want to spare you being designers the hassle of that. And who's better than Mr. Kojic to talk about motors and motor control?
So I'll call her today and find out what's going on.
Yeah.
That's the last I had, so
Yeah.
I'm assuming that's what we're doing. I don't know.
Yeah.
I'll call her.
Call her. That would be really great.
So you got some different information I got now.
Oh my God, these PowerPoint presentation. I have 2008. I got PowerPoint presentation 2008
For grounding and bonding.
for overcome protection device. 2008.
Up here, so you can go on grounding and bonding now.
And overcome protection device. Oh, okay.
Yeah.
I'm confused. I'm really confused.
Mine-
Control and motor
I don't know
control.
if you got my message.
Yeah.
I looked at my PowerPoints, they're a mess.
Yeah.
It's like, oh,
Okay, I'll swing by. We'll talk.
Oh, yeah. But I'm not gonna need you this afternoon after we have to follow that.
Okay.
I'll talk to you.
All right, we'll see you. Any comments, guys, or any questions about this, the controller? before I'm going to show you the split unit. I showed you the split unit. Here's what locked rotor current Jeff looks like. I want to emphasize a couple of things. You see where it says maximum fuse right in here, 6060 or circuit breaker hacker. These are what you're going to be looking at. They give you the full load current of the motor, rated load amps of the compressor, rated load amps, locked rotor amps. Can you guys see the locked rotor amps 164? Rated load amps 25. All this information directly from the nameplate. Directly from the nameplate. So you can see the condenser and the evaporator have different values. The most important things for us, Jamie, my friend, is this rated load amps 25, locked rotor is 165, the voltage, as well as the overcome protection device, right there.
So if you were to use it, you'd have to use 60 amp.
Yep, absolutely. And here's what you're going to be using. If you're to use it, here's your the branch circuit selection current. Either your option either to use a fuse or a circuit breaker in this case, and they have to be 60, no calculation. So what I need to do here in this case, guys, is I need my fuse here. It's going to be 60 amps. This will be 100 amp disconnect most likely. And my conductors, look at my conductors. Which voltage are we going to be using? We're going to be using 50, 58 or 240. 28, are we using 28? At the top, is it 28? Can you guys look at the, we're using 28, so that will give you the higher voltage. Then we can use this amp times 1.25 and we size these conductors. Oops, these conductors right here. That's it. They have heat strip even. So do you see how they have more equipment, guys, in it than just the motor? That's why we use the branch circuit selection current multiplied by 1.25. The fuse is given. Disconnect, no problem. How do you size it disconnect? You take this value, 1.15 times 58.6, size this disconnect. Any comments, any questions? Again, I promise you that we will be doing calculation a little bit more details than just throwing at this, but really not a whole lot to it. I can't bring to your attention, guys, is how important this system is. Why we use an implant? Because there's more to it than just a motor. There's more to it than just a motor. That's why we have to use an implant. There's so many. Look at this. I have a condenser. I have a compressor. I have an evaporator. I have a kilowatt heat strip inside it. All these are inside one big package. So that's where the minimum branch circuit selection current becomes a big deal. Okay, I don't know how many of you guys have seen this, but this can give you rated horsepower, maximum locked rotor current. I'm going to go to three-phase right away. Take this. I'm going to use one example, and I know you guys will know it immediately. One example. Take, oops, not here. Take, this is how you size the disconnect. I'm going to go, here's my disconnect here, and I need to size my disconnect horsepower once. And I have a motor, and this motor locked rotor current equal 300 and amp, and the motor is running at 480 volt. Okay, can you guys see that? I have a locked rotor current 480. Size the disconnect for this motor. Okay, Jeff, what's the voltage? The voltage is 480, Chad, so I'm going to be right here. Everybody can see where I stood. I went right in here because the voltage is 480, you go to 460. Next, what's the locked rotor current, Chad? 300. Where's 300? I have right here, I have 290, 300. I don't, so I go to the next standard up. So here's my 300 equivalent, which is next standard up. Then you go across, you go all the way across, and what's the horsepower rating of this equipment? 50. See how easy that? So this will be a 50 horsepower rated disconnect. See how they size based on the disconnect, guys? One more example. Suppose that this voltage, this one was 150 and the voltage was 208. Okay, let's go to 208. Let's go to 150. The horsepower rated is what? 10 horsepower. How easy that? Again, we will do calculation a little bit more because I need to add This is if it's only one motor. What if it's two motors? You just add them up. So I have some calculation in the spring that we do, guys. I'll prep you for the spring. We will be using this again in the spring. But if you know it now, Jeff, you're done. Any comments, any questions about the horsepower rating of a motor? When you size the horsepower, that's easier. Based on lock, this table is based on lock rotor current. Right in here, lock rotor current. Lock rotor current. For three phase, of course. There's one for single phase too. Very easy. Take the lock rotor current under the right voltage, find the horsepower. Okay. So that's my my table. We talk about this one, lock rotor current, full load amps, and the other ones, guys. These are the full load amps, 250. You're familiar with the full load amps for motors, and 250. Gentlemen, I'm going to leave you in the good hands of where. Oops. Well, what did you guys do to the chats? Okay, I will leave you in the good hands of this picture because I think we go back to where we started. Oops. Come on. Okay, it doesn't want to do it. So, we go back to where we started, guys. Okay. There you go. Okay. Evaporator takes the heat from the building, change the liquid into gas, dump the gas into the compressor compress it into high pressure, send it to the condenser remove the heat from the coil, from the refrigerant, change it back into coil, into liquid, and dump it right across the evaporator and keep going it over and over and over again. Bigger systems, the air here becomes a big deal. We can't use the air, so what do? They circulate water. Instead of blowing air, they blow water to cool it faster. And in other system, again, they start using other refrigerants.
You mean the water would be in the evaporator side, wouldn't it?
The water would be, well, the water, if it's a cooling tower, will be in the condensing side. If it's an air handling unit, the water, there will be actually two water systems. One water system is taking, instead of, see that hot air that you got here? That's a small room. What if you want a building like Dunwoody? You can't take the hot air from here and shoot it 300 feet down there, right? So what they do is they take pipes, they chill the water here, and they take the pipe to wherever you want. So now we get chilled water here, and from here, they use another water system, so they're really two water systems. This water is to cool, to remove the air outside. This water is to take the cold and recirculate it through the whole building. So there are two water systems, standalone, complete water systems. Again, I promised you we were coming to this. This will be a cooling, here will be cooling tower with it outside. You see them on the top of the roof of the building. Here will be air handling unit. You bring that chilled water to an air handling unit, again, another coil. You throw the air right through this chilled water and you get your chilled air. Chilled air. Any comments, guys? Any questions? Any comments? Any questions about cooling system? Again, next project, Jeff, we will be doing calculation about chillers and cooling towers and so forth, the whole system put together. For our project, guys, I want to remind you before I shut up, I promise. In our project, we had a chiller, so that basically we got the same thing. We have a chiller. We don't have a cooling tower. We have a chiller, and we were chilling the water to circulate it to one air handling unit. So we have a chiller, and we chilled water. We brought it to the air handling unit. We did not have a cooling tower, though. We just the chilled water circulated to the air handling unit. Or chilled refrigerant, I don't know. You could do the chilled refrigerant to circulate the air handling unit too if it's smaller system. It really depends on how big the system is. Smaller system, like central air, very simple. Refrigerant move from the evaporator to the condenser. Bigger system, you start circulating water, chilled water. Okay? Any comments, any questions? Any comments, any questions? So that
Here they consider the threshold between the two.
What's the threshold? That will be,
1,000 square feet, 1,000 square feet.
I really don't know. Like the building that we have 10,000, right? And it was specified 10,000 they specify a chiller for it. But I can guarantee you can use a rooftop units right in the top. So there's so many systems you can use rooftop units. But yeah, probably 10, 15,000 is a threshold for a chiller. Yeah. Otherwise, you can solve it with multiple rooftop units. Yeah. Any comments, any questions for chat, guys? That's all what I have for you today. Tomorrow, guys, I'm going to do my last lecture, which is going to be about renewable energy solar system. And then, you're going to miss me until the spring, huh? All right. Thank you, guys.